Right, why do I look so bright? Oh, okay, it's the lights here. All right, so hey everyone. So I think I'm just get ready to get started. So today, what I want to talk about is this sort of like empirical but yet hard question in machine learning, which is what should you set as your batch size in an algorithm? And so what is this whole business about batch sizes? Let's just cover it briefly. Yeah, so here we are. So this is the paper I want to use as a sort of case study to like explore this question in more detail. But let me just give you the high level idea of the problem. So generally, remember like when you have some sort of gradient update formula, it looks something like this, right? Like let's say your weights are alpha, and then so you're gonna say my new alpha is equal to my old alpha minus some gradient times some learning rate. Uh, right. So this is typically how you would just like update the weights of your model. So um, but the question now is like, well, this gradient thing, uh, basically it can either be uh, based on a loss from an example or a loss from a batch. So from a whole bunch of examples. So why is this distinction important? Well, typically, like when you're trying to train some sort of model, and you're gonna essentially have something that looks like this. Like let's say this is time, and then this is your loss, and you generally want this thing to just go down, right, and then eventually like hit somewhere that's close to zero. Um, the main idea with if you had like batch size one though, what's going to happen is that you're basically going to get like a curve that kind of looks like this. However, if you do the loss over like batches, then the idea is that this would be smoother because you're considering more examples at any given point in time. So one natural question is like, why don't we load the entire data set as a batch? And there's two reasons. So generally large batches are good. So why don't we just load the entire data set, right? Like there's sort of two problems with this. The first one is that like the basically the data is too big, as in by too big I specifically mean doesn't fit on a GPU's memory. So let's say this is like over 40 gigs. Uh, and the second thing is that you're basically doing less frequent updates, which means slower training in general, right? Because you're doing fewer updates, but each of these updates involve you looking at many more examples. And so overall, this is going to be much slower. So typically, like what's the heuristic? I mean, so what I use typically for these stuff, and you may have seen some of these numbers in streams. It's like extremely. Oh, I know, Susan. Okay. So typically these like you would pick the batch size as a heuristic. Like so, if let's say batch size one, this is a single example. Some very common ones I've seen are 16, 32, 128, 256, 1024, 2048. Um, so this is great and all. And so I think 128 is maybe the most common one. I've seen examples, and then 1024 I think is another. So these are the two that I see the most. But and answer questions like, well, why the hell did we settle on these values? And I think it's empirical, like basically based off of experiments that we've seen other people run, based on what's worked for me. These are also the numbers I've independently seen to be true in my experiments. And the way I typically do this is I start with 128 and I keep doubling the batch size until I see that the training time is increasing. Uh, and then as soon as it starts, the training time starts increasing. So basically, it's going to look something like this. Let's say this is say something like this. I mean, it's going to be a histogram, right? So let's say this is batch size, and then this is time to train. Typically, you'll see something like this, right? And so the idea here is that you get a lot of benefits, but at some point the performance starts degrading. And this is what I actually expect this paper to be covering. So this is a paper by OpenAI called an empirical model of large batch training, and it discusses how they go about doing the study, and it also includes the entire OpenAI Dota team, which I believe is fairly large. So here, if I'm not mistaken, like yeah, so it's like at least like a dozen people. It looks like. Yeah, I think some people that I've met here, I've met Simone, I've met Susan. Everyone else I haven't met. I think Brooke Chan is the person I've seen talk about this project the most, if I'm not mistaken. Um, yeah, so without further ado, I think like we can just get started. So this is sort of like the main background. Like why is it that, we see this sort of weird effect? Is there some sort of theory behind it? And in practice, like what should we use as our batch sizes? Like, so in an increasing number of domains, it's been demonstrated that deep learning models can be trained using relatively large batch sizes without sacrificing data efficiency. However, the limits of this massive data parallelism seem to differ from domain to domain, ranging from batches of tens of thousands in ImageNet to batches of millions in RL agents that play the game of millions. Oh, interesting. I did not know this. So basically, uh, oh, like basically, batch size is domain dependent. So there's limited conceptual understanding of why these limits to batch sizes differ and how we might choose correct batch size as a new domain. So we demonstrate a simple and easy to measure statistic called gradient noise scale. Okay. Which predicts the largest useful batch size across many domains and applications, including a number of supervised learning datasets like MNES, IFAR, ImageNet, Billion Word, reinforcement learning domains like Atari and Dota, and even generative model training such as autoencoders. So we find that the noise scale increases as the loss decreases over a training. The noise scale increases as loss decreases over a training run and depends on the model size primarily through model. So our empirically motivated theory also describes the trade-off between compute efficiency and time efficiency and provides a rough model of the benefits of adaptive batch size training. Okay, this is interesting. So there's a couple of ideas here that I think we should be on the lookout for. So one is this idea of the like it's domain dependent. The other is I'm just gonna do this like one, two. The other is where was it? The gradient scale noise. Uh, so how is this defined? And then three is adaptive batch size training. So also I do want to mention that at least here in this paper, I do this. Just want to zoom in a bit more. See if this is better. You can do one more. Okay, perfect, perfect. Sorry. Um, so the other is this idea of adaptive batch size training. So what is this about? So the idea is that like batch like increasing batch sizes is a form of data parallelism because you're effectively working with a bunch of examples at the same time. And typically for devices like GPUs, where you need to make sure that it's not bottlenecked by your I/O, so you need to give it enough data for it to be worth sending something to GPU. This is something I talk a lot about in my model and data parallelism tutorial. So there's a couple, so go check them out if you're interested. But the idea is that like there's a trade-off, right, between compute efficiency and time efficiency. Like how uh, like yeah, if you throw like a thousand, if you throw let's say 1,000 servers and train in parallel, you may train faster this way. but is it worth the compute, and when is it worth it? Like, is it at 500, is it at 50? So there's sort of a trade-off between compute efficiency and time efficiency. That's important. It's sort of like a metric of cost, right? Like, this is really, getting back to this idea of cost. So I think this is all fine and good. So let's just get to the meat of the paper. So, okay, oh wow, it's a table of contents, I see. So the theory of gradient noise, some experiments, some related work, some discussion, and some methods, and then methods for all time. So the actual paper itself is about 15 pages, but it's about an extra 15 pages for the appendix. Um, okay, right. So a major enabler has been parallelism. If model training cannot be sufficient, then it may take too much serial time and therefore be practically infeasible. Yeah, so this is a problem with model parallelism in general. Like, it's like your main overhead becomes the communication cost. So recently, a number of papers have shown empirically that on specific data sets or tasks, large batch sizes can achieve almost linear speedups in training without substantially harming sample efficiency or generalization. Oh wow, linear speedups. Batch size of 8,000, 16, 30. I had no idea batch sizes this big were being used actually. Okay, this phenomenon is not confined to supervised learning. So in reinforcement learning, batch size of over 1,000,000 time steps with tens of thousands of environments running in parallel have been used in a Dota playing agent, and even in simple Atari environments, batch sizes of several thousand time steps have proved effective. Interesting. Yeah, so they're using basically, I think the main thing I want to say here is like batch size can, up to 64K or 1 million, which is, I think absolutely absurd. But it makes sense. Like, I mean, let's do a rough of the envelope math, right? Like, let's say I come in here, and then let's say we have a size of 32 by 32 image. How much is that? Or just picking very small patches, right? Okay, let's see. So, okay, so let's say, I mean, let's make it a bit bigger then. Let's say 128 to 128. Okay, so we're gonna do lots of back of the envelope math right now, so this may not be super accurate. Just like to see if we're in the right ballpark. So let's say we have 40 gigabytes divided by 3.33 kilobytes. Well, this happens every time I stream, by the way. So we can feed a GPU at once up to 11 million images in a single batch size and probably be fine. So I guess, yeah, like this puts it in perspective, right? Like it sounds like a lot, but why not? If it can just take the whole thing in, and then just do like one matrix multiply, like I don't think the GPU is not going to care about how big this stuff is. All right. So for a given data set and model, there is little evidence in predicting how large a batch size we can feasibly use and why that number takes a particular value, and how we can expect it to differ if we use a different data set or model. So why can we apply batch size over 1,000,000 when training a Dota agent, but only tens of thousands when training an image recognition algorithm? In practice, researchers typically experiment with these, but the downside of this is that large batch sizes often require careful tuning to be effective. For example, they may require a warm-up period or an unusual learning schedule. So the fact that it's possible to use a large batch size can remain undiscovered for a long time. Where for several years, conventional was substantially smaller, knowing ahead of time what batch size. Oh, interesting. Uh, yeah, I like this point actually. Like they're basically saying that yeah, like if you're just like gonna do like a trivial, like trivially set a bunch of parameters, just increase the batch size, like you may not get better performance. And so it does take some domain knowledge, I think. And I mean, at least for me, I haven't observed an example where I can actually give a GPU like batch size of tens of thousands and have it do okay. Like I've actually never observed this before. Um, so what is this chart saying, right? So you have a compute cost, then you have a training time, and okay, so this is a square, like a rectangle for some reason, and then they're saying less hardware, smaller batches, more hardware, larger batches. Okay, and then what is this saying? So score equals 10 days of gameplay and compute cost in dollars. So the compute cost increases if you have more parallel players, right? But then, oh, I see what they're doing. Okay, okay, okay. Um, yeah, this is an interesting chart. So basically, like the what this chart is trying to show you is that you could train, like let's assume you have a fixed budget. This is the dollar amount that you can spend. Other sometimes people do this comparison in flops, as in like just how many computations can a machine do. So typically the way you would see this is that here you're saying, um, well, like let's say I can run 4,096 parallel players, and I can run this for about I don't know, like, what's 10 to the minus. I mean, yeah, you can run it for about 5 hours, or you could run for 10 hours 16. Does that make sense? But then, oh, it's more like how much would it take to converge at the cost of using more compute resources? I see. And then, so this is the blue one is clear, but what about yellow? What's going on here? Um, so the trade-off between time and compute resources spent to train a model of given performance. Oh yeah, so it is like total convergence. It takes the form of a Pareto frontier left. Uh, Training time and compute cost are primarily determined by the number of optimization steps and the number of training examples processed, respectively. So we can train a model more quickly at the cost of using more compute resources. And on the right, we show a concrete example of the Pareto frontiers obtained from training a model to solve the Terry breakout problem to different levels of performance. The cost and training time depend on the compute architecture as shown approximately. So what is it? I mean, so here they're saying, okay, well, let's say we train it only to 10. Oh, interesting. Yeah, there's a couple of interesting stuff just like in this chart alone. So basically here what they're saying is that first off, the score here is much lower, right? And so this is saying that if you train uh, for a relatively reasonable score but on a lot of machines, it's gonna work really fast. But if it's something where it's a high score, like as in it has to do really well, then you get diminishing returns essentially with more hardware. So basically, uh, like you get diminishing returns with more hardware for high task performance. All right, very cool. I mean, like this chart alone, I think probably was gonna, it looks like it's going to summarize a lot of ideas from this paper. So they attempt to answer some of these questions, and they measure a simple empirical statistic, the gradient scale noise, essentially a measure of signal to noise ratio of gradients across training examples, and show that it can approximately predict the largest efficient batch size for a wide range of tasks. So our model also predicts a specific shape for the compute time trade-off, illustrated by figure 1, and our contributions are a mix of fairly elementary theory and extensive empirical testing of that theory. All right. Should increase as models get more accurate. Then the noise. Okay. So on the conceptual side, we derive a framework which predicts under some basic assumptions that training should parallelize almost linearly up to a batch size equal to the noise scale. After which, there should be a smooth but relatively rapid switch to a regime where further parallelism provides minimal benefits. Okay, yeah. So it's like this is the diminishing returns curve that I showed here. Like it's like this is the basically this is the gradient scale noise. So, and they verified these predictions across 8 tasks in supervised learning. Um, RL, data generative models, including ImageNet, the variation autoencoders, okay. And so we also showed that the noise scale increases over the course of training and demonstrate efficiency gains from dynamic batch size. The noise scale eventually becomes larger for more performant models, but this appears to be caused by the fact that more performance models achieve a better loss. Okay. Okay. So it is. So less noisy gradient estimates allow SGT type optimizers to take larger steps, leading to convergence in a smaller number of iterations. As an illustration, we showed two optimization trajectories using momentum and a quadratic loss with different step sizes and different amounts of artificial noise added to the gradient. Less noise, smaller steps. More noise, less noise, larger steps. Oh, I see. I know this is just saying like big steps good, I guess. Yeah, so like big steps, little noise. This is good. All right. So before working through the details, it's useful to present the intuitive picture. So suppose we have a function we wish to optimize via stochastic gradient descent. There's one underlying true up. So when we perform an SUD update with a finite batch size, we're approximating the gradient to this true loss. So how should we decide what batch size to use? So when the batch size is small, the approximation will have high variance, and the resulting gradient update will be mostly noise. We'll average out the variance and push us overall in the right direction, but the individual updates of the parameters won't be very helpful. Applying them all at once using larger batch sizes. So by contrast, when the batch size is very large, the batch gradient almost exactly matches the true gradient, and correspondingly two randomly sampled batches will have almost the same gradient. As a result, doubling the batch size will barely improve the update. We will use twice as much computation for little gain. All right. All right, great. So we'll now formalize the intuitions described in 2.1. So consider a model parameterized by variables theta and RD, whose performance is assessed by some sort of loss function, and it has an average over a distribution of data points, and each point has a loss, and the full loss is given by this. But this is the loss over a batch, it looks like, and then its variance scales inversely with the batch size. So the expected value of covariance with the per sample variance. Yeah, so I guess this is just like just a complicated way of saying is large batch size. Less noise. So if we perturb the parameters at a vector, we can expand the true loss at this new point to a quadratic error. If we had access to the noise, let's true and use to perturb the parameters. Okay. Okay, yes. This is almost similar to the other figure I had, but just inverted. Um, so the noise scale is what? So it's H sigma over GHG. So our definition of the noise scale is independent of the size of the full training set. We use a step size larger than. Despite the many unfounded assumptions in the above derivation, we will find that equations 2.7 and 2.8 provide a helpful way, even when using optimizers including momentum, atom, and RMS prob. Uh, okay, let's just make sure we understand this expression. So what's H again? So H, let G denote the true gradient and H the true Hessian parameters at parameter values theta. Okay, great. So this is like the second order variations, and then sigma is the covariance matrix, it looks like. Per example covariance matrix, okay. And then what's G? A gradient estimate for the batch. And then what's H? Okay, let me just, oh, sorry. So we said this is Hessian. This is covariance. And this is a gradient for batch. Um, so the noise associated with the batch is going to be this expression. And so let's just think about this expression for a bit. So it's dependent on the Hessian of the parameters, or yes, of the parameters. And it's also dependent on the covariance uh, of all the examples, it looks like, right, at those given parameters. Yeah, so it's a covariance is a function of the parameters here. And so yeah, this is interesting. So it's not really a function of the data at all, right? Like it's a function of the gradients of the data, which is I guess implicitly a function of the data. But otherwise, like H and sigma are only a function of the parameters, which is very interesting. Uh, so one thing is a noise scale, yeah. So this is like they're calling it like this is the so this is just a noise scale here. So equation 2.7 implies that okay, so what's an piece of optimal improvement? Is the optimal step size. So an optimal, so minimizing this equation with respect to epsilon leads to this expression uh, as the optimal step size, which produces an optimal improvement and the loss from the noisy gradient. An optimal improvement from the loss from the noisy gradient. Hello? Yeah. Um, noisy gradient, covariance of. Okay, so this is interesting. Yeah, so it's also implicitly also a function of the learning rate, but I guess they just removed it here to simplify the derivation a bit. But otherwise, yeah. So if beta noise, the second term in the denominator dominates the first. So increasing the batch size linearly increases the progress and loss. This is a small batch regime. So which increases, okay, so by contrast, when B is greater than B noise, then the first term dominates, so that increasing B has almost no effect on the progress and the loss. This is the large batch regime where increases in batch sizes do not speed up training and simply waste training computation. And the switch occurs, okay, yeah. The Hessian, okay. Okay, so they just take wow, okay. So they just take the trace of the covariance matrix and then divide that by the norm of the gradients. So I mean, I'm just confused at one thing. So like basically feature covariance matrix. I mean, because it's still saying that this is a covariance matrix of the features and not of the examples, which I'm finding uh, a bit confusing. But like a trace on number of parameters will be a lot more scalable than trace on number of examples. And a trace is nice because you're just like reading elements from a diagonal. So this just takes constant time. Sorry, this takes linear time to compute and then linear time. So this is a linear time algorithm. Whereas if you're computing the Hessian, then this is a like uh, quadratic algorithm. Because for every point you're computing the derivative with respect. Sorry, every parameter you're computing the derivative with respect to every other parameter. Um, so that's why it ends up becoming like a square. Um, okay, so like let me just write some notes. So this is basically linear time to compute. And then here, how did they derive this? And we have defined the noise scale. This almost like looks like it's pulled out of a hat. Where'd they get these numbers from? Okay, so this is coming from trace of this over B. And then, but let's just get a sense of the argument again. So basically they're saying, so if we perturb the parameters from a given point of the loss function, we can expand the true loss at this point to a quadratic error. Okay, great. So we get, oh, interesting. So yeah, so perturb loss and get quadratic estimate. Okay, great. So once we have the quadratic estimate, uh, what we do is we take its expected value. And so then this is going to be, okay, the loss E of G minus epsilon of G squared. Oh, interesting. Like that's, I guess that would be true if you're perturbing it by the magnitude of the weights, which if you're saying something like, oh, it's an average perturbation, and you're also assuming like a normally distributed perturbation, and you're also assuming that the original weights are normally distributed, then this would be true. Uh, okay, I generally don't like these like normal distribution proofs because like that's very hand wavy, but okay, whatever. And so then you're taking the half of squared and then G, where is this GHG business coming from? From 2.2. Okay, so wait, the estimate of G and then the estimate of the covariance of G is this. So where is this coming from? Okay, maybe this is like out of a hat. It's like proof by magic a bit. But we'll get back to it. Like I may just be missing something simple here. But then like once you have this expression, you can minimize it with respect to epsilon. And then this is the value that you get. And then plus B noise, okay. So then what you do is like where you like epsilon opt goes away. Loss max. Okay, so they're replacing this with the optimal loss instead of the epsilon max, and then Oh, an optimal improvement in the loss. Okay, sure. And then I don't know where this is coming from. So this is also, magic. Um, okay, so I guess like we can always just get back to this, but it's okay. Like something like you can still get the point, I guess. And I think this is sort of going to be the main idea because this is like an easy to compute entity, right? So thus far, analysis has only involved a single point in the loss landscape, but in section 3, we'll show that the equation 2.7 nevertheless predicts the dependence of training speed on batch size remarkably well, even for full training runs that range out over many points of the loss landscape. So by averaging equation 2.7 over multiple optimization runs, we find a simple relationship between training speed and data efficiency. Uh, the actual and minimum number of possible steps taken to reach a specified level of performance. And E and E min represent the actual and minimum possible number of training examples processed to reach. Since we are training at fixed batch size, we have expected of total. Oh, I see. Expected total is equal to B times size of total. Okay, yeah. So the number of examples you're gonna go through are the number of total basically steps times the number of batch sizes. So this makes sense. And so then they define the critical batch size by an empirical fit to the above equation as uh, the minimal number of examples divided by the minimum number of steps. Interesting. Okay, so this is interesting. And I think let's just do some quick Googling on critical batch size at this point. So the point at which compute efficiency drops below 50% optimal, at which point training speed is also typically 50% of optimal. Between experience and training time needed to achieve a given score is predictable. Oh, I see. This is actually a good summary right here. Interesting. Yeah. So large batch sizes become more useful later in training as the noise scale increases. Um, yeah. So the idea here is that like when it comes to the very end, you want to be making like a few similar steps and you don't want your loss to change a lot. And so that's why larger batch sizes would make sense. And then small batch sizes train most efficiently. So as in if you want to go through your data as few times as possible, I would imagine batch size 1 is best. But then if you want to train fast, then large batch sizes are a lot better. And so this is very interesting. Like, all right, very cool. Let's get back to the paper. Where was it? Okay, great. So sorry. As a hyperbolic shape, represent figure 0.21. Okay. The mathematical arguments in the previous section depend on several assumptions and caveats, and it is useful to list these in all one place. So the stricture in 2.2 strictly local pictures. It tells us how to best improve the loss on the next gradient step. Really choosing the best local improvement is generally not the best way to optimize the loss. For example, greedy optimization might perform poorly in the presence of a bad local minima. Poor conditioning, parameter values oscillate about like in a non-predictable way. Uh, Simplified noise scale. Oh, I see. Yeah, so this is basically this argument with like the like with the Gaussian, because it really is just an estimate. This is here like Hessian can be ill conditioned. We still didn't talk about learning rates. A quadratic approximation basically takes in the Hessian, which is second order. But you may want to take in like higher order moments, like basically the derivative of every point with respect to three other variables. Higher order. Okay, so and here they talk about like large batch sizes uh, can be bad for generalizing. So this is sort of, I think, like a tangential point. So we're not going to go into this point in a lot of detail. Uh, B will grow when the gradient decreases in magnitude as long as the noid stays roughly constant. Since G decreases as we approach the minimum of a smooth loss, we'd expect B to increase during neural network training. Oh, I see. Yeah, so remember the formula, right? So it was trace of sigma over G squared. And so as the gradients as the gradients increase, then the critical batch size will decrease. And so you need to have a smaller batch size. But I guess that conflicts with what I understood earlier, so maybe we'll get to that point in a bit. Um, so weak dependent on model sizes. So the number of model parameters in the neural network cancels in the noise scale. So we do not expect B to exhibit a strong dependence on model size at fixed loss. All models that achieve better loss will tend to have a higher noise scale, and larger models often achieve better loss. So in practice, we do expect larger models to have higher noise scale, but only through the mechanism of achieving better loss. So I thought that was what sigma was about. Did I misunderstand sigma? Is it just noise? Okay, this is fine. Okay, so you can figure out the critical batch size with the simple formula. The noise scale can vary significantly over the course of training run, which suggests that the critical batch size also depends on the chosen level of model performance. And the noise scale depends on the learning rate via the temperature of training, what is consistent between well-tuned runs. The trade-off between speed is controlled by the batch size. Yeah, I think I was going to summarize this myself, but this is a great summary. All right. So now they do a whole bunch of experiments. So the critical batch size above which scaling efficiency decreases significantly. It's interesting that autoencoders are so low, right? Like how come? Why is Dota so high? Like, so it looks like the more complicated. Because I wouldn't expect this to be. Is this simpler than other tasks? Is that why? Let's see. So the optimal learning rate is displayed for a range of batch sizes. For an SVHN classifier trained at HGD, the optimal learning rate initially scales linearly as we increase the batch sizes, leveling off in the way we predict behavior. Optimal learning rate. Best learning rate, best fit. Okay, so the darker batch sizes are small batches are efficient, larger batches are fast. Oh, interesting. Yeah. So what was SVHN? Oh, that's the training. The Street View house number data. So I see. It looks like it's fairly popular. Google Street View. All right. Yeah, this is another, I think, important chart. Okay, so more experiments. Let's see. The typical noise scale approximately predicts the batch size at which returns from increasing scale begin to diminish significantly. So we provide a detailed discussion of our methods. So here it's eTrain. So wait, what was eTrain again? It was the examples, I think. Yeah, examples processed, and then optimization steps. And this is the loss that is achieved. It be critical, be simple, be noise. Be critical. Oh, I see. So there's about like it's like a 10x difference, maybe 100x. Let's say about 10x, right? Difference between the simple and the be critical. Generative modeling, okay. So as expected, VAE had a much larger be critical and be simple as compared to the autoencoder, and both models had much lower be simple. So Y is expected. Uh, yeah, the scale of experiments is massive in this paper. Like we're not even halfway through and not even done any of the experiments. Um, yeah, part. Those are in the higher noise scale for Dota 5 and 5. I mean, yeah, like this is like I expected this would be because like my understanding was like they for a single training runs like they spent about 6 months worth of compute. So I don't see them like doing this for all batch sizes. Uh, and then at different error boundaries. So one thing I'm curious about why these quantities vary by 6 orders of magnitude. I mean, that is like a substantial difference, I guess, but all right. So it also predicts how the optimal learning rate scales with batch size, although those predictions are not as precise. So it allows us to use the noise scale from a single run, and across tasks, it tells us the largest useful batch sizes for a task is likely to be correlated to informational notions of the complexity of the task. Because the noise scale essentially measures how diverse the data is, which is one aspect of task complexity. Oh, I see. I mean, then that's a good heuristic, right? So, like, basically, the more complex task, higher batch size. Okay, while B simple roughly matches B crit for all data sets, the ratio can vary by about an order of magnitude across tasks. This may not be surprising, since B simple does not take into account Hessian conditioning or global aspects of the loss landscape. But it would be very good to get a better understanding of this ratio. It was smaller than 1 for the autoencoder, roughly equal to 1 for LSTMs, and greater than 1 for both image classification and Atari. And we lack an explanation for these variations. It would certainly be interesting to study these ratios. Due to its crucial role in data parallelism, we have focused on the batch size, presuming that the learning rate or effective temperature will be optimized after B has been chosen, and our theoretical treatment focused on a specific point in the loss landscape, ignoring issues such as the relationship between early and late training and the necessity of a warm-up period. It would be interesting to address these issues insofar as they may provide motivation for adaptive batch sizes. Oh, is this how they measure it? Systematic searches, symmetric. We separate. Okay. Okay, so they're just like for each of their environments, they're just being very specific around the kind of experiment that they did. These are cool charts, though, in general, of more Atari tasks. Atari Qbert, Dota 1v1. Okay, so I see true skill 30 versus true skill 50. So examples, oh, I see, okay. So in terms of examples processed. And I think for, where's Dota 5v5? Critical batch size at the start. Oh, as an average, I see. Toy model for temperature. Okay, so the whole adapting batch size thing, they just have it in the appendix, it looks like. I may just do this like another time. Comments deterministic training performs poorly. Okay, some preliminary tests of generalization. I see. So in the appendix, like I'm sorry, I'm just gonna summarize. So the like in the appendix, they address this issue around does this generalize well? Uh, I'm assuming they're saying like we want to further investigate this. They you need some sort of learning rate schedule, and then here we can follow on significant. Oh, interesting. I actually like this trick. This is important. Not only it should have been in the appendix, like basically adaptive uh, gradient setting. Because like be simple. I mean, what's R again? I think it's just a constant between 0 and 1. And then here, okay, dynamically varying the batch size. Okay, basically saying learning rate is some sort of temperature and some noise on this. B noise is equal to noise simple. Okay, and then like tons and tons of experiments showing for basically here it's like E like here like so this is basically the harder like they I think this is the easier tasks and then this is the harder tasks in yellow. I think because they switched the convention, so it's sometimes confusing to read. Um, yeah, I think this is all harder. Actually, no, because no, sorry, yeah, it's the other way around. So, uh, I think here it's like the easier ones are here because you're processing less examples and you're training for less. But if you're processing a lot of examples, then you need to train for more steps. So this is the compute and efficiency trade-off here. So one thing I'm still curious about, uh, so when they say we know B critical, they're saying by an empirical fit to the above equation, which is the minimum number of examples divided by the minimum number of steps averaged over training on. Oh, I see. Okay. So this is uh like empirically obtained. And that's how they compare B simple to this later. You can just compute this over multiple training runs. So that's fine. And then there's still this sigma is bothering me because sometimes they call it noise and sometimes they call it the per example covariance matrix is defined as okay. So it's the gradient uh of the loss with respect to some parameters. Okay. And then to get the covariance of this thing, you take the expected value of the product minus the the square of g, or like the magnitude of the gradients. I see. But how come this is independent of the model size? Oh, because I mean, so the loss is either like a scalar or a vector, and then same for, like this g. Actually I believe this g is a scalar, and then this is a scalar. So this whole thing is actually a scalar. No, it's not a scalar. It's actually a matrix because we're taking the trace of it. And so that means that if it's a matrix, then this is a matrix as well. And if we're multiplying two things and getting a matrix back, these are also, this is also a matrix. Actually, wait, let's go back to G. I mean, G looks like a scalar to me, so it's the sum over all elements in the batch of the loss with respect to each parameter in the loss. Oh, so this is an xi where xi is drawn from P. So it's going to be a vector. And then I guess like a vector multiplied by its own transpose will give you a matrix. Is that right? So let's say import torch, and then A equals torch dot tensor. And then this is 1, 1. Right. And then how do you do transpose in PyTorch? Okay, torch dot transpose B equals torch dot transpose A. So it needs a dimension. Does this work? Oh, it needs dimension 0, dimension 1. Okay, let's say 0, 1. This work. Print B. Okay, great. So now if we do A times B. Okay, yeah, that's what I figured. So yeah, sorry, I just sometimes get confused, just need to double check. So this is a vector for sure, but once you multiply this vector by another vector, its transpose, you're going to get a square matrix. So you have the square matrix and you're subtracting it with something that's a loss with respect to something else. So this is also going to be a vector multiplied by its transpose. It's going to be a square matrix, then square matrix, and then each of the, okay, great. And so when you're taking the grade, okay, so why are they calling this noise then? So because it's the per example covariance matrix. If, if we had access to the noiseless gradient G and use it to perturb the parameters, then equation 2.4 would be minimized by setting this. Let's minimize the expectation with respect to trace of sigma. All right, so the traces is going to be a scalar, but then like what's going to be actually like what does it mean here? These values that are inside of it. So it's going to be like the pairwise interactions between all the features in the model, right? So, oh, so oh, I see what they mean. I see what they mean. Okay, okay. Sorry, this took me a while. So basically, even though like regardless of the size of the model, be simple, which is just trace where was it? Which is just traced of sigma divided by G. This is not a function of the the number of parameters because it's gonna be a scalar. However, sigma is obviously a function of the parameters uh, because it's a square matrix, the size like where each row and column is the size of the number of parameters. Same, and then G is also a function of the number of examples in your batch. So this is also a vector. But once you take the norm and square, then this becomes a scalar. Scalar divided by scalar, that gives you a scalar. Um, and so this is like sort of I guess like a neat heuristic. And I think that it would be nice. Like, do they have like a library for this, like torch critical uh, batch size? Interesting. Yeah, so this is back to this point of generalization. It's unclear, I think, whether this is true. It may just need like another empirical paper. Um, and so I think that's going to be it, actually. So to sort of summarize, um, let's do this. So to sort of summarize like a bunch of results from this paper, I generally want to say that it's hard empirically to figure out like what is what is a good batch size to have. And so typically people use a heuristic where they vary this thing from 16 to I don't know 2048. But in this paper, people go up to like a million or hundreds, like tens of thousands, like a million in the case of Dota, tens of thousands in the case of image data sets. So you can increase them quite a bit. And increasing them is hard because you also need to adjust your learning rate. You need to make sure you're still making as many passes over your data set. I really like this paper. I really love these graphs they have about Pareto efficiency, where you fix a given task performance you want to get, and then you plot the compute versus the cost efficiency of a model, and then see how it varies. The main, I think, takeaway for me at least is that there's a very simple heuristic to help you figure out like what should the batch size be at every step, and it's basically called the critical batch size. It has a complicated formulation that depends on second order derivatives like the Hessian, but you can simplify this expression to the simple critical batch size, which just takes the trace of your feature covariant matrix, and it divides it by by the norm of all of the gradients in a given batch. And this gives you a good heuristic for what the batch size should be, and they've validated this empirically in a whole bunch of experiments. So I think I think it's a really good paper, and so it's something I want to be thinking more about. And I think as a sort of takeaway for me, I do want to start looking into how I can use this heuristic of a critical batch size in my actual experiments. That way, instead of thinking about what the batch size should be, I could just make it just like another hyperparameter that needs to be optimized. So I hope you enjoyed this as much as I enjoyed presenting it. Stay tuned. I think I'm going to be doing very soon another episode on graph convolutional networks, like their theory, how they're implemented, and then how to benchmark them using the NVIDIA Visual Profiler. So thanks again, guys, for watching, and I'll see you soon.